interested in something in the SRAM, then I can do my read-write with respect to that position in the SRAM. Alright, so connecting the LED latches, so this is just a picture that you can look at for yourself, but we have the different LEDs over here. We have the data coming in, and you effectively just store it, and that will that will feed into the LEDs, and that will give the on and out pattern. If I want to push in new data, then I need to make sure I have this latch signal, so which was, there it is, which is this particular signal, to indicate that I want to now overwrite whatever I had in here with the 8 bits data that I will now read from the bus. So this is a way to connect those particular, to connect the processor not just to memory, but also to other peripherals that can be considered as addressable, objects. So use addresses for that as well. You have some specific address decoder logic for this configuration, and you have the usual multiplexing of data and address lines. So I hope that you really understand this, and there is in the advanced problem set a question about this, a different configuration. You would do the same thing. Alright, so what about memory management? And so there's this translation between the logical address space and the physical address space, right? So the memory management unit, usually, right, that's what it's called in our processor architectures, handles the address translation. And what can happen? Well, the physical memory can be larger than the logical memory, and in that case we use the idea of banked memory. We divide the physical memory into n partitions that we call banks, and the size of each of those is equal to the processor's logical address space. If the physical memory is less than the logical memory, in other words, I would actually need lots more storage, but I don't have it because my physical memory is too small, well, then we talk about virtual memory. The logical memory is essentially it's virtual memory. It exploits the entire logical memory space of the processor, and what you will have to do is that if the physical memory is just too limited, so what you need to do is, for example, that if it's not in your DRAM, you need to go to disk in order to load it. So what you have to do is, you need to do on-demand loading of data blocks to the physical memory from some secondary storage, like a disk to DRAM, for example. And that's what we call paging. So the disk storage plus the DRAM is, of course, now larger or equal to the logical memory. Now, besides just managing the logical to physical address translation, you will also be interested in protection of memory regions. So, you want to figure out whether someone else is trying to get to the memory who should not be going there. You want to manage that. There's maybe other kinds of things like encryption, like verifying that it was not tampered with. You want to isolation of tasks and threads implies that you need to prevent unauthorized access between the memory spaces of the threads in a multitasking system. So there's a bunch more things that you want to think about. Now, let's talk about banked memory for a moment. So suppose, the question is, suppose I have 512 kilobit memory on a 16-bit address bus. Alright, what's the problem? Well, what we see here is that, so how do you want to do the mapping? That's the question. So the first thing that we realize is that if you would create 16 memory banks of 32 kilobits, then 512 kilobits will be available to the application. So effectively, the 4 most significant bits of the 19-bit physical address indicate which memory bank I'm going to be interested in. So 512 kilobits would be like 19 address bits, and the 4 most significant bits are now the ones that are indicating which memory bank we're talking about. So this needs, of course, also some software control. You need to understand from the software side how this address translation actually works, what you're doing. But the point here is that we will have, again, address bits, data bits, and we are now going to use, because we really need 19 address bits, we're going to use these data bits, and we essentially multiplex those in a way that they can also give another bunch of address bits, like our, oh that's wrong, A16, A17 and A19. Okay. Oh no, that's correct actually, sorry. This is correct. So we essentially, in this simplified picture, we just copy over address 0 to address 14. So that's 15 bits, and then you have another 4 bits which come out of these 4. Anyway, there's many solutions, but the point is that I want to show you that you can actually now multiplex the data lines in a way that it actually is helping adding more address lines, because you need those in your mapping from logical addresses to physical addresses. Okay. So I've talked about quite a bunch of things, so let's go back to this important picture though, so and then we can go to the rest. Are there any questions about this? So I've talked about quite a bit, right? So we first talked about the processor, we talked about pipelining, we talked about connecting this with the actual memory, and what that involves with wait states. And you can look at the data sheet, you see this diagram, and you need to look, of course, at the data sheet for your SRAM. You need to find out how much wait states you need to include in order to make it work. Now once you understand how this works, you can add a bunch of other peripherals. Here we call these latch 0, latch 1 and latch 2, indicating 3 strips of 8 LEDs. But how do you address those? Well, you want to have your 16-bit address space, and you want to be smart about it. And so we assign a whole range of addresses to latch 0. Doesn't matter which one I'm using, but the point is now that I only need A15, A14, A13 to distinguish which of the 3 peripherals I need or the SRAM. And then we talked about multiplexing these particular pins to both support transmission of data or reading of data and transmission of address bits. So you'll be asked to do something similar for some other configuration, something else over here in your problem set. So I hope this is somewhat clear. Okay, so let's talk about, since we talked about advanced topics, let's talk about what next semester is going to talk about. So what we see here is that we are going to talk about this parallel bus interface. We start with that actually. So now you will be doing a problem set about it, but next semester we're actually going to build it. So you will have some external SRAM that we want to connect to the MCU, and we also want to connect an OLED display to the MCU, and you will need to do a smart multiplexing. And of course the lab that talks about this and the lab that talks about this has quite a lot of material in it in order for you to be able to do so. We'll be talking about the CAN protocol, and you actually do an assignment on this. We'll talk about wireless protocols, and we'll talk about Bluetooth in particular. The lab will be about Bluetooth. Then we'll talk about analog sensors and motor control. That's all part of one lab, but you already know a lot about it after this particular block that you'll be doing at the end of this semester. And effectively we're going into more depth in real-time operating systems, and you will be able to use the parallel bus interface with the graphic OLED display and the Bluetooth implementation that you did with your analog sensor interfacing. You may or may not use material out of real-time operating systems. You can combine it all together to do your final project, which is this collision avoidance robot. So a robot that's going to that you can steer. It goes around the room, but it will sense if it's getting close to an obstacle, and it will stop, or it's doing something of your own choice, or you decide for yourself you want to add to this particular collision avoidance robot something that you like to think about yourself to make it your own project. And that's essentially what we're going to talk about. Now, there will be some case studies too, that's the whole idea, but the point is that you will do a lot of this type of connecting, you building this whole thing yourself. So you'll actually be buying this thing together with what you already have in this particular semester, and you'll be able to combine it all together. So this is actually so I will not talk too much about that, but the point here is that you would have learned in this semester pretty much all the basic understanding that you need, especially interrupt service routines and all that kind of stuff is super important. But now, in this particular semester, the advanced course, you're going to actually build your own libraries for a couple of those things. So you're going to build a library to interface with the SRAM. Yeah, you just need to first of all put the hardware in the right way with the proper decoder logic, but then you also know that in order to talk to your external SRAM, I need to follow a certain sequence according to that time diagram in the data sheet that we just saw. So you will be waiting for a little bit, and then you will be setting a certain ping to high and then low, and then you can do your writing or your reading and so forth. So you're going to build the write and the read functionality yourself in the library according to your own hardware configuration. Well, essentially you will just copy what we have in the slides, but the point is then that you're going to translate it into a library that you can then call. For the graphics OLED display, a similar thing. You're also going to create a library for that. So that's kind of new, and you will be really looking into the data sheets to really understand how those diagrams work and how do they then translate into actual code that leads you to, read and write from memory or display things on the OLED display. Now, for the CAN protocol is outside, not connected to the final project at all, but it is a very useful thing to know. So you're going to actually have a lab assignment to communicate in this particular way. The Bluetooth stuff, again, you're going to do that yourself, of course with help from the assignment slides, but the whole point is that you again look at the data sheet, you work it out in a way that you can then communicate. Then look, sensors, interfacing, motor control and all of that, you will be busy in this particular lab, in the project that you're doing in block 6 for this course. Well, that will pretty much automatically translate also into how you would work with this assignment. And then we go into much more depth in real-time operating systems, where we talk about, we will have one assignment that talks about a certain type of scheduling methodology. So you get our code and you're going to play with that a little bit just to see how that works. We're talking about FreeRTOS, which is used in a lot of these embedded systems. So you should then be able to run that as well. And thirdly, the idea is not yet done, but hopefully we'll be able to do it, to work with yet another real-time operating system and then actually do an assignment on that as well. We have a couple of case studies and your final project. So these case studies and final project should probably be 1/3 of the semester actually at the final part. So say the final 4 weeks or something like that. And then all of this is in slots of maybe 3 weeks and 3 weeks. These are a little bit more difficult, and maybe 2 weeks and so forth. You still need to figure that out, but that's how that would work. Yeah. Any questions about this? I think maybe 1 or maybe 2 have signed up from this class, or 3, 2 for sure. I didn't look at the latest count, but anyway, you're most welcome to join this. Any questions? All right, cool. All right, let's go to the lab, and then you can continue your work.